In the last two lessons, we described how to determine the VSEPR geometry and the Lewis structure of a molecule. Watch those videos first if you have not seen them yet. This lesson will continue and show you how to assign formal charges to each atom in a molecule. In this lesson, we'll use the Lewis structure of SO2 obtained in the last lesson as an example to show you how to assign formal charges to atoms. To assign formal charge to an atom, we compare the number of electrons assigned to it in the Lewis structure to the valence electrons it had originally. The difference is called the formal charge. Notice that the formal charge is what it says it is. It is formal and has no real physical connection to any measurable. In case there are several possible structures for the same molecule, the formal charge is a useful rule of thumb device to help us determine which structure is most stable. To assign electrons in the Lewis structure to atoms, we follow these two rules. 1. If an atom has a lone pair, both electrons are assigned to that atom. 2. If an atom forms a bond with another atom, it gets half of the electrons. Every atom in the Lewis structure has a formal charge. Its formal charge is equal to the number of electrons assigned to it minus the number of valence electrons it had originally multiplied by -1. The sum of the formal charges over all atoms must equal to the charge of the molecule. We will assign formal charge to each atom in SO2. The sulfur has one lone pair, which is 2 electrons. It also has 3 bonds, which supply 3 electrons. So there are 5 electrons assigned to it. It has 6 electrons originally, so its formal charge is 5 minus 6 times -1 equals to +1. For the oxygen on the left, it has 2 lone pairs, which is 4 electrons. It also has 2 bonds, which supply 2 electrons. So there are 6 electrons assigned to it. It has 6 electrons originally, so its formal charge is 0. For the other oxygen, it has 3 lone pairs, which is 6 electrons. It has 1 bond, which supplies 1 electron. So there are 7 electrons assigned to it. It has 6 electrons originally, so its formal charge is 7 minus 6 times -1 equals to -1. In this structure, S is in the center, but there is actually another possible bonding structure which has the same chemical formula SO2, but in this alternative structure, oxygen is at the center and sulfur is on the outside. We will use formal charges to determine whether this alternative structure is more or less stable. First, we need the Lewis structure of this molecule. You can easily see that swapping sulfur with oxygen does not change the Lewis structure. But now, whether the double bond is on the left or on the right makes a difference. So what used to be 2 resonance structures now become 2 distinct Lewis structures. We assign formal charges to both. On the left, sulfur has 6 electrons in the Lewis structure and it has 6 originally, so its formal charge is 0. The center oxygen has 5 in the Lewis structure, but it has 6 originally, so its formal charge is +1. The other oxygen has 7 in the Lewis structure and 6 originally, and its formal charge is -1. On the right, sulfur has 7 electrons in the Lewis structure, but it has 6 originally, so its formal charge is -1. The center oxygen has 5 in the Lewis structure and 6 originally, so its formal charge is +1. The other oxygen has 6 in the Lewis structure and 6 originally, so its formal charge is 0. The stability of a Lewis structure depends on the formal charges in this way. 1. Atoms prefer as little formal charge separation as possible. 2. If formal charges cannot be avoided, then the most stable structure would have the negative formal charges on the most electronegative atoms and the positive formal charges on the least electronegative atoms. The electronegativity of an element is a measure of how badly it wants electrons. In general, the atoms on the top right of the periodic table has the highest electronegativity, but excluding the noble gases, which have no desire to attract electrons and have very little electronegativity. Oxygen, being higher than sulfur on the periodic table, has higher electronegativity. So out of these two structures, the oxygen would prefer to have the negative formal charge than the sulfur, and the first structure is more stable. Finally, comparing the structure to the top one, we recognize that the top structure is more stable because the +1 formal charge is on the sulfur, which is the less electronegative element, and out of all three, the structure is the most stable.